Uh, actually, the session is on additive manufacturing, but actually my presentation is not exactly in the domain of additive manufacturing, but I think it's a much broader domain, what we call the rapid manufacturing. So we started with rapid prototyping, but as Pedro also told that the area has grown so much that people now talk of additive manufacturing as such a separate domain. But there are various other processes which work rapidly, which started primarily with the prototyping purpose, but now they are producing components which are ready to be used. And one such technology which I'll be talking about I'll be talking about a brief part of that particular technology because there are so many aspects of this technology, and that we call as the incremental sheet forming process. So the title of my presentation is Development of Thickness Prediction Strategy and Incremental Forming for Improvement in Part Evaluation. Satwik is my research fellow, and Saurabh was my undergraduate student who's now doing masters in computer science in US. So this is my organizational presentation. I will be starting with the introduction of the process, then we'll talk about briefly the background and the methodology, and then I'll focus more on 3 different test cases to stress upon the methodology which we have proposed. Incidentally, we have a couple of patents also on this particular process, and finally we'll be concluding the discussion. So additive manufacturing, as all of us know, is basically when the material is being added. Rapid prototyping or rapid manufacturing, where you are producing components in a faster manner. So this particular process, which we call as the incremental sheet forming process, which we also popularly call the die-less manufacturing process, is basically a type of a forming process without any dies. So it saves the time of die design, die building, testing of the components. So what the process is basically, you have a sheet, you start with a CAD model and you locally deform the sheets in an incremental manner, just like any other CNC process. The basic process also starts with a conventional CNC machine, like this is a conventional 3-axis CNC machine, which we have adapted for our purpose. So from the CAD model, we generate the tool path. The tool path is given to the CNC machine. The sheet metal is clamped from the sides, and based upon the geometry of the component, the tool path moves and gradually deforms the component as per the process. The physics behind the process is basically localized plastic deformation, and these localized plastic deformations, they are dragged along the entire geometry, but then they have their own consequences also. So this is still not, to be very honest, this is still not, the process still not reached to the commercial level. A lot of still many challenges are there, and one of the major challenges is basically the structural accuracy and the ununiform thinning of the sheets. So our work is focused on how to control the ununiform thinning. So this is a basic process mechanics, as I told you just now. We start with a CAD model. From the CAD model, we generate the tool path on any of the CAM software. Incidentally, in our purpose, we have developed our own CAM software because we want to integrate the thickness prediction module also. And then that CAM module, the tool path, goes to any of the forming machine. We can use a conventional CNC machine also. If we want to go with single point, there are multiple processes. Like if you're using only one tool, it's called a single point incremental forming. But I can have a couple of tools moving in sync. So that is a 2-point incremental forming or duplicate incremental forming. So we have designed and fabricated a machine also, which can do, because none of the conventional CNC machine can manufacture this component. But I'll be focusing more on single point incremental forming, because that's easy to understand at this point of time. So these are some of the components which we have fabricated in our laboratory, and they are very close to the actual components, but still there are certain challenges which I'll be telling you. So to predict the thickness, as I told you, the 2 major challenges are the geometrical accuracy or structural accuracy and the non-uniform and uncontrolled thickness variation. The sheet becomes thin at certain sections which you cannot predict initially. So to avoid that ab initio thickness prediction, there are certain techniques already available like sine law, mesh-based area calculation, volume constancy model, but all these are failing in one part or the other. Like for example, most of these methods require a separate CAE module. So you cannot integrate a CAM module with a CAE module. You have to fetch data from one, go take to any CA software. Like we have also done this work. We worked on ANSYS, we worked on even Altair also, we tried on Abacus also. But then when you are porting data from one system to another system, number one, we talk of a rapid manufacturing, but it takes time from porting data from one system to another. So rapidness is gone. And then there is loss of data also. So we wanted to have from the CAD model to the finished component. So these methods fail on that aspect. Then most of these methods cannot be used, they're good when you have a axisymmetric components with wall angle relatively less. So as soon as you go beyond a very high wall angle, maybe more than 75 degree of wall angle, these methods fail. And these methods also are not suitable for a component which has a varying wall angle, maybe something like a dome shape of component. And meshless methods are also applicable, but then they try to find out the area of the entire component in totality. So they are also limited to only axisymmetric components. So the methodology what we are proposing is very simple methodology. So what we do is that rather than calculating the area of the entire component, we let's say this is my component, I'll break this component in multiple slices, and I'll take a pair of slices which I say call a slice set. So we'll be doing this implementation to find out the area only on a pair of slices, what we call a slice set. So we'll keep on doing this till we reach the last, because last doesn't have a bottom one, and then we'll add these areas and volumes to find out like what is the thickness prediction or what is the loss of the thickness. So the methodology consists of generation of horizontal slice sets, then the calculation of incremental area, which will include calculation of floor areas and calculation of wall areas, and then based upon that the calculation of predicted thickness. So this is like the generation of horizontal slice sets, which we start from the STL file. STL file is generated based upon the CAD model which we have. So you can see these are like multiple slices. So one pair of slices is what we call a slice set. So first slice set, second, third, fourth, and this will be my last nth slice set. So each slice will have a top flow and a bottom flow and the wall, which I'll show you in the next. And this is for the hexagonal prism. It can be for any other component also. So this is like my one slice set. So this is my top slice floor, bottom slice floor, and the wall. And the thickness is basically the desired incremental depth. Like normally we do something like of maybe 500 microns. So this is like so, but it all depends upon because the smaller the slice depth, the time taken will be more. So depending on the complexity of the component, we decide the step depth delta z. So if delta z is so you can find out like the depth of the component divided by delta z will give me the number of slices. So these are the three things: top slice, bottom slice, and the wall, which will help us in finding out the area. So now what happens is when you, like for example, when you slice these components, the data points, the corner points they come are very erratic, something like this. But for the efficacy of our methodology, what we want is that number one, there should be uniform number of points on like these points on each two consecutive slices, and they should be equally spaced. So the first step what we do is that we reparameterize these points on these slices so that the u value or the v value, whatever you say, they should be uniform, and between multiple slices there should be uniform number of points. So we have to merge certain data points, we have to add certain data points so that this becomes uniform throughout. And the best thing about this particular advantage is that the entire algorithm works on the concept of incremental thing also, as well as discretization also. So unlike like mesh based method where you have to triangulate or discretize the particles, here there is no need, because now using green algorithm we have these linear segments. So I know like these are my points. So just by using the green algorithm, I can find out the area which is enclosed by this contour. So, but for the calculation of the wall, we have to go for triangular patches, because these are the number of points on the top floor, these are the number of the points in the bottom floor. So there are uniform number of points, like as you see in the TMC logo also. So we have both continuous method as well as the discretized method also. It's a combination of both to find out the area between the two things. So how do we calculate the thickness then? What we know is that this was my initial thickness, the initial area. Now when this slice was performed into this, so what actually happens is that this bottom slice is undeformed because the entire thinning takes place in these walls. But this is my initial volume, this is my final volume, and the sum of this will be equal to the volume of the top will be equal to the volume of the bottom as well as the volume of the wall. But we also know that since this area is undeformed, so the thickness over here is same, which is TF. The only thinning is taking place on the walls. So this helps me in calculating the wall thickness. So just to prove it, we will do, I'll show some 3 different test cases, starting with a simple axisymmetric geometry with a wall angle. This is a model of a truncated cone with a depth of 35 millimeter, base diameter 80 millimeter, and wall angle of 60 degrees. So when we did this, and the second is an axisymmetric geometry with a variable wall angle. The radius at the top is 150 mm, depth is 50 mm, and the wall angle is varying from 50 degrees to 0 degrees. And finally, the third case is a component with a, it's not only like non-axisymmetric, but it's also a varying angle. So we have a radius of convex surface, length of flat surface, and all this data is being there. So this is basically an irregular hexagonal prism, what we have tried to do it. So there is a discussion. So if you look at these 3 figures where we have done the simulation and we also done the experimentation. So the actual component will form on a aluminium 1050 sheet of 0.91 thickness. The tool which was used, this tool was what we call the indenter, is a ball shaped tool having a diameter of 8 mm. The incremental depth, because we want to understand it faster, so we have taken a relatively larger incremental depth of 1 mm. The feed was 2 meters per minute, the spindle RPM was 1000, and we have simply used a hydraulic oil as lubricant. And based upon these are the photographs of the actual components being formed on the conventional CNC machine, a truncated cone, dome shape, and irregular hexagonal prism. So when we compare the existing algorithms, our algorithm, and the experimental data, you can see, like for example, if you talk about some axisymmetric component with a constant wall angle, the sine angle will obviously give you a constant value of thickness. This is the experimental value, and this is the value given by our algorithm. Seems to be larger distance, but much better, because particularly when you look at the other 2 cases, we'll see. So if we compare the percentage error which is being given by the sine law is varying from 2.917 to 7.912 with an average of 4.6, and the percentage error given by our algorithm is varying from 2.4 to 7.22 with an average value of 4.4. This doesn't seem to be very encouraging, although it's within the limits, but the other 2 results are much better. Now if you look at the geometry's variable wall angle, particular dome shaped component, so this is the data being given by sine law. This is the data being given by the experimental result, and you can see this is the data which is given by proposed algorithm, and you can see this is very close to the experimental data. So average is also reduced from 3.234, which is given by sine law, to just 1.6%. As for even if you look at the min max, also it is also for just 0 to something like 4.16, which is the maximum error. And then when you talk of asymmetric geometries, the irregular hexagon, again this is the value given by the sine law, the experimental data, and the one which is being proposed by our algorithm. So again, the errors are, like for example, rather than 10.4, which is the maximum error, in our case the maximum error went to 7.538%, and that too for the particular depth. And there might be some aberrations in the experimental data also. So just to summarize what I have presented, so we talk about a algorithm where we try to find out Number one, not only the thickness prediction, but the important thing is the same algorithm was meant to predict the tool path. So I can parallelly generate the tool path and find out what is the thickness variation at different points. So we talked about the three different cases. For the constant wall angle, the average thickness as per the sine law was 0.455 mm, and this was constant throughout the wall. While experimentally, the data varied from 0.465 to 0.491, with average thickness of 0.476. Our technique proposed the thickness varying from 0.453 to 0.458 millimeter with average of 0.45 mm. So you can see that this variation is also shrunk, and the predicted percentage error is less than 0.5%, which is within the acceptable values. Now if you go to the variable wall angle, which is for a dome shaped component, the sine law predicted 0.8145 mm as the average thickness, and the experimental data showed varying from 0.64 to 0.91 with average thickness of 0.79 mm, and the proposed algorithm showed a variation of 0.643 to 0.91 mm with average of 0.78 mm, and then this again resilience is even less than 2%, which is very good as per the industry practices. And if you go to asymmetric geometry, the average thickness as per the sine law was 0.665 mm. Actually, it was varying 0.65 to 0.91 with average of 0.7, and our algorithm gave a variation of 0.64 to 0.91 with very close values, 0.67 and 0.74, and that too, in this case also, it is like 4% of approximate 4% of the error between the things. So to conclude, so we have done, I have shown this variation for the three different geometries: frustum of cone, irregular hexagon, and dome shaped component. And for frustum of cone and irregular hexagon, the thickness decreases with increase in depth. So as you make a deeper component, there will be lesser thickness. While for the dome, initially it decreases and then it increases. The reason is that when you decrease the radius of the dome, basically the wall angle decreases gradually from top to bottom. And so for all the values, for all cases, the values of thickness which are predicted by our algorithm were in good agreement with the experimental values. And from the results obtained, the validity of the method proposed can be safely established because we have done it for asymmetric constant wall angle, asymmetric variable wall angle, and an irregular component also. And obviously it can be extended to other geometries irrespective of their shape and symmetry. So these are like some of the references which we have used, and thank you very much for your patient hearing.